denatured by heating them in a sample loading buffer containing reducing agents. Reducing agents like beta-mercaptanoate or DTT, dithiotretol, and the sodium rhodocyl sulfate. Then, after we just denature the protein, we just cast the gel in a vertical stand, and then we just load the sample and sample in the well, which is in the staking. The gel has been protruded in the staking gel, and then we just this varies from protocol to protocol. So the constant thing is like we run it at 200 volts for 30 to 40 minutes. That's enough for the protein to run through the gel.
But you did not mention the dye.
So everything, I just in the next slides.
Next one.
Yes, sir. So
sample कर दिया तुमने dye तो तुम next में देखे आ रहे हो
dye के मुन्नाडी आत्मनो sample
yeah you have already loaded the protein in this
no sir this is like this is sample we just denature it. So after once we done with gel run and we just stain it with a Kamu blue stain which just stains the protein Kamu blue stain which goes and binds with these particular protein things and it makes us to visualize it and then we just destain it later. And now we have to.
What is the use of this? Using the dye? You just
visualization, sir.
For what?
The particular protein. This Kamu's blue dye has the ability to go and form. Goes and binds with the protein.
That I know, but I want to know this for these people. These 2-3 people are sitting in the what? Why? Without dye you can get it done. It's a harm. Can't you do that?
Sir, all these.
And you can still later on. Initially, what is the first step? I mean, you are talking right.
Yes,
but
yes.
Another application of that. Why you are using the dye here itself?
Tracking purpose.
Tracking is that.
You yourself have already mentioned.
Sir, bromophenol blue we use it for tracking, sir.
Why? I mean, say this is because when you are running the gel at that time, the bands are coming down.
Yes,
it will flow off if you cannot visualize the proper band. It will flow off. It's a flush off and you won't get anything. So it is the basically for the demarcation.
Sir, that's what for that we use bromophenol blue. That's a tracking dye. That I will mention it later.
And what is the
this is staining dye, sir. Once staining the particular.
Yes. You are using for the gel staining.
Yes,
right.
So once you are done with the STS phase, we just cut the gel according to the size of the blot or the PVDF membrane to blot it over it, and just further continue with the Western blotting. So this is a standard protocol which I got it from source book. This is a percentage of gel. So these are the solutions which are used to cast the gel. So acrylamide, bisacrylamide. So next slide I'll just tell what are these purpose of these solutions. So just numerical values which we use it for perfect thing. So tris it has been used as a buffer. So buffer range, it has a buffer range of between 7 to 9. So its pKa value is at 8.3. So what is pKa? pKa is the pH at which the ions is off dissociated. So glycine. So we use this glycine. Glycine has been used as a source of trailing ion or the slow ion. The mobility of the glycinate is such that the effective mobility can be set at the value below that of slowest known proteins of net negative charge, the pH range. The minimum pH of this range is approximately 8. So this actually goes and binds protein, which actually trails or like slows down the speed. That's it. That's the purpose. And acrylamide. Acrylamide is a basic the gel which we are going to cast it. Acrylamide is nothing but it's a white crystalline powder, which it's a monomer. When we add, it's a monomer. When we add more amount of this acrylamide, it forms a polymer. The polymer is not that much intact, or they just slides over each other.
For the complexity of the gel.
Sir?
For the complexity of the
For the
gel.
complexity.
So to form a gel, we need something sturdy and something intact, so tight. So that means gel. So here in this case, it's just what do you say? Just a polymerization takes place. We need some cross-linking agent to make this so intact so that it forms a gel. Okay. For that, we use this bis-acrylamide. Bis-acrylamide is nothing but it's a 2 monomer of acrylamide attached to its head-to-head region. Okay, so that's it. So sodium rhodocyl sulfate. So while using this acrylamide, be careful because it's a neurotoxic, so causes some problem. Then sodium fluorescent sulfate. STS is a most common dissociating agent used to denature native proteins to individual polypeptide chains. When a protein mixture is heated to 100 degrees in the presence of STS, it just denatures. And next comes ammonium persulfate. We need some initiator to start the reaction. Reaction in the sense the polymerization of the gel. So ammonium persulfate acts as initiator, it's a catalyst. And the temmer is actually added to facilitate the activity of the ammonium persulfate. So to get a more thicker, more sturdier gel, we just alter the concentration of APS as well as the temmer. So in STS page we have these two types of the stacking gel and the dissolving gel. The stacking gel is the one which comes in the upper part, and the dissolving gel is the one which comes in the lower part. So the stacking gel is the large pore polyacrylamide gel. So we actually can adjust the pore size in the gel. How we go about it is like acrylamide and bisacrylamide, so that forms an polymerase reaction cross-linking over taking place, and it forms a gel. So if you add a less amount of this bisacrylamide, so there will be a loose cross-linking, so the size of the pore will be high. So once we increase the concentration of the bisacrylamide, so it forms more intact, so the pore size can be reduced. So that's how we design the pore size, but I don't exactly know what's the size of the pore.
But it's based only on the protein.
Yes, of course. But average protein which can be resolved is like 110 kilodaltons or something. I just studied. So the pH range of this taking gel is 6.8, and this gel is cast over the dissolving gel. The height of this stacking gel region is always maintained more than double the height and volume of the sample to be applied. Double the height of the sample to be applied. Then comes the dissolving gel, which is at the bottom. The dissolving gel is a small pore and small pore polyacrylamide gel. Compared with the staking gel, the dissolving gel pores are a little bit smaller, so that the proteins which run through it get separated based on the molecular weight. They go due to the porosity, they just go and intact in the pores and just bind it. In the dissolving gel, the proteins separate according to the size. Dissolving gels have an optimal range of separation that is based on the percentage of monomer present in the polymerization reaction. So this is an example. So for 8% dissolving gel, we can get a protein between 24 to 205 kilodaltons. So that are the examples. So this is how the setup will be. Here we have the dissolving gel or the separating gel, and here we have the staking gel, and we form the wells using the cope in which we are going to load the sample. So this is the whole setup. This is a vertical setup. As once we add the STS, the protein gets the negative charge, so it must obviously go towards the positive charge. So the positive charge comes at the bottom and the negative charge comes at the top. And this is the buffer which we use to run the reaction. So as I earlier mentioned about the denaturation, so once we get this is the native form of protein which we are supposed to get it down to this form. So we can perform this STS page. So the proteins are basically first denatured by heating them in a sample containing buffer, sodium fluorescent sulfate and beta mercaptoethanol, which is an reducing agent. And then the proteins now they no longer have the secondary, tertiary or the quaternary structure, so it forms this kind of thing. The resultant protein taken rod-like shape and the uniform negative charge is over the protein to the mass ratio proportional to its molecular weight. So this is how the protein will resemble once we load. So what is sample loading buffer and what does it contain? It contains a tris buffer to provide the appropriate pH, SDS, sodium fluorescent sulfate detergent to dissolve the protein and give them a net negative charge, glycerol to make the sample sink into the wells. What it does is like once we load the sample, there is a possibility of spilling. So what this glycerol does is like it gives them density gradient. It just gives a density gradient so that it exactly goes and sits in the well. So that's the purpose of using this glycerol. So bromophenol dye is to visualize the tracking. Beta mercaptoethanol is used to break the disulfide bonds. So how does this migration of this protein takes place in the electric field? Because they are negatively charged proteins, they move towards the positive ion. The migration of the protein is directly proportional to the overall charge of the protein, that is negative charge, and inversely proportional to the protein size or the molecular weight. So this is how the STS phase setup has been made. and here we just denature it, we run it, and we get the bands based on the molecular weight. Once we load the markers in the left hand side of the one corner, based on the molecular weight, it is separate.
Why the temperature is an essential and crucial factor in the when you are running gel?
Sir?
What is the role of the temperature crucial when you are putting the gel?
Putting the gel, where, sir?
When you have caused the gel,
yes, sir.
now you want to run the gel,
yes, sir.
the protein. You have to go for the stabilizer or the power pack, you have to stabilize the temperature also for volts. So why it is necessary? Why?
Why we keep it, maintain a temperature particular?
Temperature,
while casting the gel or like running the gel?
When you are running the gel.
So the proteins, there's a possibility of again the breaking of the bonds, denaturation. So the basic structure primary structure which we load in this as a sample is a polypeptide chain of amino acids. So there's a possibility of breaking, but I just went to the net in that they specified like cysteine which has a sulfate bond. So in that polypeptide chain, if two cysteines are sitting next to next, so they obviously they'll form the sulfate bonds, disulfate bonds. So there's a possibility of breaking while we're using that beta-mercaptol. So to avoid denature, we must maintain a particular temperature, that is a lower temperature. So that's what we run the gel in 4 degrees.
I'm not talking about the temperature. I'm talking about the voltage which you
Voltage.
supply to the power pack.
Voltage.
Yeah.
Optimize it.
That's optimizing, sir. That varies. Higher voltage, lesser time. Lesser voltage, higher time.
Yes.
So this is Western loading. Western loading is used after a similar term, the Southern loading, which was invented by E.M. Southern in the year 1975. So identification, this is the basic definition. Identification of a specific protein in a complex mixture of protein can be accomplished by technique known as...
Why you are using Southern? Yes, you.
Okay.
So
Why you are using Southern loading? What for you are using?
for DNA,
And Western?
so for proteins.
ठीक है चलो मैं सोच रहा हूँ तुम लोग सुन भी रहे हो नहीं चलिए.
So this is called a Western blotting. So in Western blotting, it detects the antigenic determinants of the protein molecule using antibodies, and often is described as similar blotting. The antigenic determinant is the epitope in case of antigen and the paratope in case of antibody. The paratope comes in time with the epitope. So that's the basic
concept.
So these are requirements that, to carry out the Western blotting. Okay. This is what I mentioned. This once we run the gel, we can find the band. This is because of presence of the bromophenol. Okay, you just take it out. Just place it over the apparatus. We just form a sandwich, and then we. This is actually a semi-dry apparatus, which doesn't have the flow of buffer fully. So the instrument over there is an wet apparatus in which we soak the sandwich inside the buffer. Where in this case, while using the sandwich, we use a filter paper as well, Markman filter paper. We just soak it in the buffer and then we use it. So it's a semi-dry. In that case, it's a wet. So that's it. That's the apparatus difference. So this is the methodology. Once we run the gel, transfer it to a transfer buffer and also place the PVDF membrane in the methanol solution for some time. Why do we place this PVDF membrane in the methanol solution? Is like to activate the force. So once we get from the company, it will be, it's not activated. So just to activate, to just dip it in the methanol solution for some time. So soak the filter paper in the transfer buffer and lay flat. And now we just soak the PVDF membrane in the transfer buffer and lay it flat over the filter paper. Now place the gel. Care should be taken that the gel bands must intactly go and sit on the PVDF membrane, so that the efficient blotting can be taken place. And then lay the gel again with the filter paper, soaked in a transfer buffer. Now using a paper, just roll over the sandwich to avoid to avoid this trap air bubbles to get away from that. So which can be hindrance during the blotting. So transfer the sandwich directly to a transfer apparatus in case of semi-dry, as we saw the previous diagram, and or to a cast in a case of wet transfer. Place the gels with a membrane on the anode or positive electrode, usually red, and gel on the cathode or negative side. Gas should be taken. The anode side, the gel must be placed on the anode side, and gel must be placed on the anode side, and the gel must be placed on the cathode side, and this thing must be placed on the anode side, because the transfer is taking place from negative to and positive. Understood?
Gel in the where do you place the gel?
Place the gel with the membrane on the anode. Membrane on the anode, positive side, and the gel on the cathode, negative side.
Okay.
Correct.
Why so?
The transfer takes place from positive to negative to positive.
What transfer? What transfer? DNA.
Routing, blotting the transfer.
Like cake.
So now power the apparatus and blot for 3 hours at 60 degree volts or overnight at 35 degree volts. So after the transfer, mark the blot and then wash it with, this is the washing step, 4 times for 5 minutes with a PBST and 1 time for PBS. And after washing, add a 6 ml of blocking buffer to block the non-specific sites in the membrane, and probe the blot with a primary antibody and incubate in the rocker for 2 hours. This is 2 hours for the primary incubation. Okay, and then after the 2 hours is over, wash the blot 4 times for 7 minutes with a PBST and 1 time for 5 minutes with a PBS. Now again add the blocking solution with an appropriate amount of secondary antibody tagged with an enzyme. An enzyme may be alkaline phosphatase or HRP conjugated antibody. So that's it. These are 2 types of enzymes which we commonly conjugate with the secondary antibody. How it does is like we use a cross-linking agent called SPDP. Succinyl.
In fire and
We also use biotin amidan
Biotin
system.
is different. This is cross-linking. Succinyl para SPDP.
SPDP.
So what it actually does is first we react SPDP with the antibody. SPDP has a succinyl group which leaves and forms a SH bond, which will be in the one end, and the other end will be bound with this antibody. Again, we take this SPDP and we just react it with enzyme. And again, the succinyl group leaves, from where this enzyme comes and joins. And other again, we have this SH bond. Once we take this
Antibody
PDP and enzyme PDP, this SH, they just form a disulfide bond. So now it's conjugated, right? Understood? Cross-link. So that's how we do it. And incubate the blot on the rocker for 1 hour at the room temperature. Now wash the blot 4 times for 10 minutes with the PBST and 1 time for 5 minutes with the PBS. Now we just develop now the steps are over. Now we just tagged or made the antigen to bind with the primary as well as the secondary. Now our job is to visualize where the band is present in the
blot.
Developing the blot with the respective developing methods depending on the secondary antibody. So how does the blotting take place? Basically, electrostatic force. And once we perform this sandwich, we just close the cassette, right? Cassette. So there will be some pressure. So that's also a reason for blotting. And then the porosity of the membrane. How porous it is. So analysis and detection of the Western blot. These are the several types: calorimetric detection, radio labeling detection, fluorescent detection, and chemiluminescent detection. In calorimetric, we know the calorimetric detection method depends on the incubation of the Western blot with a substrate that reacts with the reporter enzyme. Peroxidase, I mentioned earlier, right? Arsenic peroxidase, alkaline phosphatase. So all this. That is bound to secondary antibody. This converts a soluble dye into insoluble form to different color that precipitate next to enzyme and thereby stains the membrane, which we can visualize it. So after this thing, we just go for the densitometry thing for evaluating the intensity of the band. Densitometry, right? So on order the spectrophotometry, beat Lambert's law. So all this comes. Radio labeling. We can detect the proteins using this radio label tag to an enzyme. So tag to an antibody. So that's it. Previously this method has been followed where we use in iodine 125 isotope. Okay. So the disadvantage over this method is it's health it causes ill to because it's a carcinogen.
Carcinogenic. Fine.
Radiation.
Fine.
Radioactive. So that's the reason. So fluorescent labeled fluorochrome, as he spoke about the fluorochromes, no? So that method also can be applied over here. So what we use in our lab, what we do is like chemiluminescent detection, where we use a chemical as a substrate to form a luminescence with respect to the enzyme. That's what we do. Okay. So blood development, chemiluminescent method. So when you are using an alkaline phosphatase tagged to a secondary antibody, is a green color? Dark room. So when you are using the alkaline part, each enzyme has particular substrate to react with it to give the color. So in case of alkaline phosphatase, we add this 5-bromo-4-chloro-3-indolyl phosphate or the nitro-blue tetrazolium to the blood till it is just submerged in the substrate solution and incubate the blood in the substrate for 10 to 30 minutes to visualize the bluish purple color. Stop the reaction by washing the strip in several changes of water. Address the strip and photograph it or scan it in an X-ray. When we are using HRP conjugated secondary antibody, for that the substrate is available commercially, the reagents 1 and 2. What we use over there is luminol and luciferase and
luminol. It forms luminol molecules.
Luciferase and luminol. So HRP is an enzyme. So for which the specific substrate is there, in which we use to visualize the thing is like luciferase and luminol, right? So once they incubate the blood with gently shaking the substrate for 1 minute, take the forceps and lift the blood for substrate and then drain off, just visualizing. Once we are done with the visualization, wrap the blood to a saran wrap and place the blood in a film cassette, X-ray film cassette, and close it, and we get the exposure of the photons, creates impression over there in the X-ray sheets, so we can find the band. So all these things should be.
This is
we can't find the band over here.
Minute
band. So this is so all this process should take place in a dark room, obviously, because all of it. So expose the film to the blood for various times and develop the films. Okay. So that's it. So once we use the blood for one time, we can reprobe it and we can use it for further purpose. For that, we have this specific stripping buffer, and the following protocol should be followed to strip this. So this is how the band will be seen in case of stage phase, which after blotting it to a western blot, the PVDF membrane, this is how it takes place. This is an stage phase gel, the bands, it's been blotted onto a PVDF or nitrocellulose membrane, particular thing. So this is how it looks like. So interpretation of the results. Negative results is presence of no band. Positive is presence of band corresponding to the marker of our interest. And the intermediate is like any bands present but do not meet the criteria of our interest. So Western blotting advantage is like specific interaction of antigen and antibody can be directly visualized. Disadvantage is technically demanding, expensive, subjected to interpretation. So once we are experienced, if you are not experienced, if you are beginner, pro, amateur, difficult for you to analyze the results. So application, the most widely used application of this procedure is the confirmatory test of HIV, where the Western blotting is used to determine whether the patient has the antibody that react with one or more viral proteins. And next is the Western blotting is used for definitive test for bovine spongiferum encephalopathy, which is also known as mad cow disease. And the Western blotting can also mad cow disease, prions virus. So Western blotting can also be used to evaluate the proteolytic activity since it allows the identification of desired proteins using an antibodies. So limitation in case of Western blotting is like the success of Western blotting depends on the availability of suitable antibodies, perfect antibody for a perfect, specific antibody. In HIV diagnostics, this can be used as an supplementary test, not as a confirmatory test. So that's are the limitations. So this the whole thing. Done. Good.